Hi everyone, welcome to Unit 5, and we're going to be talking more about acids and bases, specifically about their reactions. This first video we're going to talk about making a buffer, and then we're going to titrate that buffer and see what happens. So, example 1. So this whole part right here, I just want to point out, we're going to be making a buffer here, part A through D, making the buffer. Okay, so part A. Consider the reaction between acetic acid and sodium hydroxide. And by now, I'm sure we've all memorized acetic acid, which is vinegar. Make sure you memorize that if you haven't yet. But here it is. So HC2, H3O2, plus sodium hydroxide. So this is asking us for a net ionic reaction. So we know that sodium is going to be a spectator ion. I'm just going to leave it out. So I'm just going to write the hydroxide. And that's going to go to my acetate. And there would be a sodium on this side as well, but again, it would be the same on both sides, so we left it out, plus H2O. Alright, so that's our balanced net ionic equation. It's all balanced. Okay, if 40 mils of 0.1 molar acetic acid is combined with 30 mils of 0.1 molar sodium hydroxide, calculate the moles of each substance, assuming the reaction goes to completion. So first, let's calculate, and you're going to have to write really small right here. So first, let's calculate moles of acetic acid. Okay, we can just take our volume, multiply it by molarity. So the volume of this, we added 40 mils. So in liters, it's 0.04 liters times 0.1 molar. And that means that I have 0.004 moles of that. Okay, moles of hydroxide now, do it the same way. So how much did I add? 30 mils and 0.1 molar. So 0.03 liters times 0.100 molar. And I get 0.003 moles, not molar, moles. Now I'm going to go ahead and do my ice table, see what happens when I combine the two of these. So writing the equation for combining these, I have, here I can do this in a different color so we can see the difference here. HC2, H3O2 plus hydroxide, so the vinegar plus the hydroxide that we see up here. And that's going to go to our acetate, C2, H3O2 minus, and I'm just going to leave the hydrogen, or sorry, the water out, because that's a liquid. So the ice table, ICE, starting here with 0.004 moles, starting here with 0.003 moles, and I haven't made any of that yet. So, assuming this goes to completion means at least one of these gets totally used up. So the one that's going to have less is going to get all used up, and there's going to be a little bit left of this. So, minus 0.003 minus 0.003, and so I picked 0.003 because that was a smaller number. 0.4 minus 0.3 is how much is going to be left over of this, plus 0.003. Your ending numbers are 0.0010 and 0.003. Hope you can see that. Okay, that's my ice table. For the reaction in part B, which is the limiting reactant, acetic acid or sodium hydroxide, and why, we kind of already said it, but it was sodium hydroxide because it was all used up. There were fewer moles of it and it was all used up. Classify the reaction mixture in part B as either an acid, base, or buffer. Why does your answer in part B not reflect the actual reaction mixture? Well, we kind of already said it, but this is a buffer, and we can tell it's a buffer because we have an acid and its conjugate base. So the acid and conjugate base is a buffer. Now, this whole system is actually going to need to go to equilibrium now because we have some amount of weak acid that's still going to just dissociate on its own. So this is not the final reaction mixture because the whole thing, the buffer system, needs to go to equilibrium first. Oh, and we said this was a buffer solution. Okay, because the buffer system needs to go to equilibrium. Whenever an acid is combined with a base and at least one of them is strong, we can consider that the neutralization reaction will go to completion. However, if one of them is weak, then an equilibrium process follows. So basically when you have either a weak acid or a weak base, you're going to get an equilibrium process. For any of these processes, 1, find the moles of the initial substances. First, you're going to find the moles. 2, use stoichiometry to describe the reaction mixture when the reaction goes to completion, and then use their concentrations for the equilibrium step. Okay, so let's learn this through an example. So, example 2, suppose a 0.1 molar sodium hydroxide solution, and that of course is strong base, is added to 40 mils of a 0.1 molar acetic acid solution. The acetic acid is weak. Gives us the Ka of our acetic acid here, and it's asking us to find the pH of the solution. So first, for part A, no sodium hydroxide has been added. So the only thing we're doing here is an equilibrium step. This is the same ice table and Ka problem that we've used before. So really, since no sodium hydroxide has been added at all, we're just seeing how much of the acetic acid is going to dissociate. So this is our equilibrium step. And this is just our acid solution. So we'll solve this the same way that we've been solving these kinds of problems. We'll write an equation, use an ice table, and the Ka. So I have my acetic acid, HC2, H3O2, dissociates into hydrogen ions plus acetate. Go ahead and make your ice table. Okay, so we have, and these are molar concentrations, so I'm going to write molar here just so we know we're not talking about moles, we're talking about moles per liter. So here we have our 0.1 molar sodium hydroxide. Nothing's been added yet, so we just have our 0.1 molar acetic acid solution. So 0.10. Of course, at the beginning, nothing is dissociated. Minus x plus x plus x. And we get 0.10 minus x, and then we have our two x's there. Okay, we know then we use Ka equals products over reactants. So hydrogen ions times C2H3, O2 minus. And my reactant, and we know our Ka here. It gives us our Ka. So we are going to do equals 1.8 times 10 to the negative 5, and then we're just going to plug everything in. So we have x times x, which is x squared, over 0.1 minus x, and because again this is a weak acid, as we've been doing all along, we're going to ignore this x, assuming it's a very small amount when compared to 0.1 molar. So this would just be divided by 0.1. And then overall you get your x is equal to 1.3 times 10 to the negative 3. Okay, so that's our x. But the problem is asking find the pH. So in all of these we're going to need to find the pH. So pH is the negative log of the H plus concentration. So pH equals negative log of H plus. And here's our H plus, that's X. So pH equals negative log 1.3 times 10 to the negative third, which when you plug in, you end up getting is 2.89. Okay, so there should be nothing new about this kind of problem. This is just an equilibrium step. No sodium hydroxide has been added at all. Okay, let's see what happens when we do add some sodium hydroxide. So when we add sodium hydroxide, first we're going to find our moles of our initial substances up here, and then we're going to use stoichiometry, and then use concentrations in our ICE table. So here I'm going to go ahead and find the moles. So this is going to be my stoichiometry / reaction step. So in this step, I'm going to find the moles. So I'm going to go ahead and find moles of acetic acid first. So in this, you have your volume of acetic acid, you have your molarity of acetic acid, so you can simply multiply the two. You can go ahead and show the units for these canceling out, but to save space, I'm just going to multiply the two. So 0.04 liters is how much we added, so we had 40 milliliters. I just went ahead and converted that to liters in one step. Multiply it times the molarity of acetic acid, so that is 0.10 molar, and that gives you 4.0 times 10 to the negative 3 moles. Okay, now let's find the moles of hydroxide. For here, when we're adding sodium hydroxide, we don't care about the sodium at all. It's just going to be a spectator ion. We do care about the hydroxide because that's what's going to end up partially neutralizing our reaction. So let's find the moles of hydroxide. So we know how much hydroxide was added, 10 milliliters, or 0.01 liters. And we know the molarity of it. So up here we're given 0.1 molar sodium hydroxide, 0.10 molar. Multiply those together, 1.0 times 10 to the negative 3 moles. So step 1, done. We found the moles of initial substances. Step 2, we're going to use stoichiometry now to describe the reaction mixture when this goes to completion. So I'm going to do that using an ICE table over on the side. So I'm going to write my equation. So I have my acetic acid plus my sodium hydroxide, which I'm going to represent with just hydroxide, going to acetate. I have my ICE table here. Now I'm not going to write this in moles. I'm just going to go ahead and use millimoles, because 4.0 times 10 to the negative 3 moles is just 4 millimoles. 1.0 times 10 to the negative 3 moles is 1 millimole. So I'm going to write that here, millimole. Remember, milli is 10 to the negative 3. And we're going to fill in our numbers. So the number of millimoles of acetic acid we're starting with, our initial, which we figured out here, is 4.0. Our hydroxide that we're starting with is 1.0. And we haven't formed any acetate yet. Change, which one are we going to use up? So we're going to use up the one with less. So here we have 4 millimoles available to react. We only have 1 millimole available to react here. So we're going to use up all of our hydroxide. So that means I'm going to subtract 1 millimole from each of these. So minus 1.0, minus 1.0. That means we're also going to produce that same amount of acetate. So this would be called your limiting reactant, just as review, because you had less of it, right? And all of it got used up. So doing the math at the end here, we have 3 millimoles of acetic acid left, no hydroxide, because all of it got converted to acetate, and we have 1 millimole of acetate. Okay, so that was our equilibriums, or that was our stoichiometry step. Okay, next step, we have to see what this is at equilibrium. So this is an equilibrium step next, so this is step 3. Equilibrium step. And so you'll notice that this is a buffer at this point. So you have both your acid and you have your conjugate base in solution. So since this is a buffer, we can go ahead and use the HH equation, the Henderson-Hasselbalch equation, So again, you didn't have to memorize that. It's on the back of your periodic table. pH equals pKa plus log of the conjugate base over the concentration of the acid. And I have all the information I need for this. So my pH equals my pKa. If you don't remember where to get pKa, remember that lowercase p just means negative log of Ka. Our Ka is up here. So we need the negative log of 1.8 times 10 to the negative 5. Once you plug that in, you should get that the pKa is equal to 4.74 plus the log of the concentration of A minus. This is a molar concentration. So our A minus over here, our ending concentration, is 1.0 millimoles, which is 1.0 times 10 to the negative 3 moles, divided by the acid, HA, which is this acetic acid right here. So we have 3 millimoles, or 3.0 times 10 to the negative 3 moles. It doesn't really matter if you use moles or millimoles here, because as long as they're the same, they're going to go ahead and cancel anyway. So go ahead and take the log of this, add 4.74, and you should get that your pH is equal to 4.26. So that means after you add 10 milliliters of sodium hydroxide to the solution, before you added anything, you had a pH of 2.89. Now you added 10 mils of 0.1 molar sodium hydroxide. Now your pH is all the way up to 4.26. So go ahead and flip your paper over. And let's take a look at part C. When you add 20 milliliters of the sodium hydroxide to solution, let's take a look at what happens. So we're going to follow our same steps. So this is the stoichiometry step first. Stoichiometry / reaction. And the first thing we're going to do is figure out the moles of both things we're starting with. So moles of acetic acid. And that's not going to change. We still had the 0.04 liters, and we still had the 0.10 molar. So we still are starting with 4.0 times 10 to the negative 3 moles, or 4 millimoles. How many moles of hydroxide am I adding this time? Very similar as before, the last calculation. The only thing is this time you're adding 20 milliliters, so 0.02 liters, and it's that same molarity. So you get 2 times 10 to the negative 3 moles. Let's go ahead and set up our ice table. So our acetic acid plus hydroxide will yield acetate. Initial change. And ending, and this is again in millimoles, just for space-saving reasons. So we're starting here with our acetic acid being 4.0 here, our hydroxide being 2.0, and we haven't formed any acetate yet. So this isn't 20 more mils on top of that 10 mils from part B. This is like a fresh problem. So overall, after 20 mils has been added. Okay, our change, look for the one with less. This is a 1-to-1 ratio, so we're going to use up all the hydroxide we have, minus 2.0. You're going to produce 2.0, and go ahead and do your math at the end. So we have 2 millimoles of acetate, of acetic acid, 0 moles of hydroxide, and 2 millimoles of acetate. Notice something here. So notice this. The concentration of your acid is equal to the concentration of your conjugate base. So the concentration of your weak acid equals the concentration of your conjugate base. So that's important to notice, and we'll see why in just a second. Okay, so that was our first step. So let's go ahead and do our equilibrium step. And again, you have a buffer system here because you have your weak acid and the conjugate base both present. You can go ahead and use the Henderson-Hasselbalch equation. So pH equals pKa plus the log of A minus over HA. Plugging this in, your pH is going to be equal to, and we figured out the pKa in the last step, So that was 4.74 plus the log of A minus, which is your acetate. So we'll just go ahead and do millimoles here. 2 divided by your millimoles of your acetic acid. So you'll notice here that this is just 1, right? And so the log of 1 is going to be 0. So 0 plus 4.74, your pH then just equals your pKa. So that equals 4.74. That's your pH. Now, that's always true anytime your weak acid equals your conjugate base concentrations. So that's at the halfway point. At the halfway point, that is when the concentration of your weak acid equals the concentration of your conjugate base, the pH will simply equal the pKa. All right, let's look at part D. At this point, 40 milliliters of sodium hydroxide has been added. So we're going to do the same thing that we have been doing. So this is our stoichiometry / reaction step. All right, so again, we're going to find moles of both. So moles of acetic acid, HC2, H3O2. And we've been finding that, so I'm just going to write it down. We found it in the last 2 problems. So 4.0 times 10 to the negative 3 mole. And then moles of hydroxide here. Let's see, at this point, we've added 0.04 liters, and it was at 0.10 molar. So we also have 4.0 times 10 to the negative 3 moles, and you can kind of see where this is going. So let's go ahead and write our reaction here. Our acetic acid plus your hydroxide is going to yield acetate. And this is millimoles again. So here we're starting with 4 millimoles and 4 millimoles. We haven't formed any. Now we have the exact same amount of both. Neither one of these is going to be limiting. They're going to both be used up. So minus 4.0 plus 4.0. Your final concentrations, you have no acetic acid, you have no more base. All you have now is 4 millimoles of the conjugate base. So at the end, there's no HA, there's no OH minus, none. So your concentration of this is 0. So your concentration of this, 0. Let's go ahead and find your concentration here of your basic ion. So let's go ahead and find the concentration of your acetate. C2, H3, O2 minus. This is the only thing that's going to be contributing to pH at this point, because this is the only species in solution. So we have 4.0 times 10 to the negative 3 moles of this. So the concentration is moles per liter. So 4.0 times 10 to the negative 3 moles. Remember, I added this 10 to the negative 3 because this is millimolar here. 4.0 times 10 to the negative 3 per liter. So this is going to be your liters of your total solution. So that means you have 40 milliliters of sodium hydroxide that you've added already. And then at the very beginning, if we look at our beginning of the problem, it says that we started with 40 milliliters of acetic acid. So 40 plus 40 is 80. So we have 80 milliliters. And when this needs to be in moles per liter, so we need to go ahead and put this in liters, 0.08 liters. So that's how we figure out the concentration of our acetate ion, moles per liter. When you divide that in your calculator, you end up getting 5.0 times 10 to the negative 2 molar. So that's our concentration of our acetate ion in solution. So since that acetate ion is the only thing that is going to contribute to the pH, we have to see what it does. So it's going to dissociate in some way. This is going to be our equilibrium step. So that acetate ion dissociates on its own. It does some reaction of its own, producing some hydroxide ions. So we're going to go ahead and write that reaction now. So we have our acetate, C2, H3, O2 minus, And that's going to be plus H2O. But that's a liquid, so we're not even going to include that in our ice table. And that's going to go to some acetic acid plus hydroxide. Because remember, it's going to rip off a hydrogen from H2O, forming acetic acid, and then the leftovers of H2O, which is hydroxide, is what's left over here. So initial, change, ending. These concentrations are molar, so we're already in molar, so we're going to stay in molar. So here, you have 5.0 times 10 to the negative 2 molar. I'm just going to write that in decimal form. You can leave it in scientific notation if you want. We haven't formed any of this. We haven't formed any of this. So as we've done before, plus x minus x plus x plus x. Here, 0.05 minus x is your ending concentration. You end with x of your acetic acid and x of your hydroxide. Okay, so now we need to go ahead and figure out what this x is. And we're going to do it the same way we always have. Remember the K expression. Since our reactant here is a base, this is the conjugate base, and remember it's acting like a base because it's accepting a proton from the hydrogen there, we need to use Kb. We only have the Ka of the acid, so we need to go ahead and figure out what Kb is first. So our Kb equals Kw over Ka, which of course Kw is always 1.0 times 10 to the negative 14th. That's the K of water. Our Ka was given to us at the beginning of acetic acid, 1.8 times 10 to the negative 5. Plugging that in, you get your Kb is equal to 5.6 times 10 to the negative 10. And that's the Kb we're going to need to use later on. So let's go ahead and write our K expression over here to the side. So Kb equals your products over reactants. So your product here is your acetic acid and your hydroxide ion divided by your reactant go ahead and plug in all our numbers for this. So our Kb equals, let's see, these two together are x squared, and we're going to ignore this x again, assuming it's very, very small. So Kb equals x squared over 0.05, and then we said our Kb was equal to 5.6 times 10 to the negative 10. Multiplying these two together and then taking the square root to find x, we can see that x is going to be equal to 5.3 times 10 to the negative 6. Now that x, what does that mean? What does that equal to? That x is telling us the hydroxide ion concentration. So that's the hydroxide ion concentration. We cannot find the pH directly from the hydroxide ion concentration, but we can find the pOH. So if you'll remember, pOH equals negative log the concentration of our hydroxide. So our pOH is equal to the negative log of 5.3. This is our OH. 5.3 times 10 to the negative 6, which should equal 5.28. Now, remember, the problem is asking us for pH, not pOH, but we can directly go from one to the other by subtracting from 14. So pH equals 14 minus 5.28, which is equal to 8.72. So there's our pH. So there were a lot of steps for part D because we didn't have any of our hydroxide left over. All we had was a weak base being left over. That weak base then underwent its own equilibrium step, and it produced a little bit more of the acid in its own equilibrium step. We could figure out how much of the hydroxide that it gave off when it produced its acetic acid, figured out the concentration of hydroxide, and from that we figured out pOH and pH. Okay, so let's look at the very last problem, part E. When we add 60 milliliters of sodium hydroxide, we're again going to start with our same steps. So this is our stoichiometry step. reaction step. First, we're going to find the moles. So the moles of our acetic acid, which we've been finding, is 4.0 times 10 to the negative 3 moles. And then moles of hydroxide. So when you multiply the two numbers together, you multiply the 0.06 times the 0.1 molar, you end up getting 6.0 times 10 to the negative 3 moles. And we're just calculating that the same way that we've been calculating all of the previous problem steps. Okay, so let's take those numbers and go ahead and figure out our reaction in our ice table over to the side. So this reaction, we have acetic acid, and we're adding some hydroxide to it, and we are forming acetate. This is the same reaction. And here, this is going to be in millimoles again, just to make it easier. So we have 4 millimoles of our acetic acid. We have 6 millimoles of our hydroxide here. We haven't formed any acetate yet. So this is going to be my limiting reactant now. We have fewer moles of your acetic acid. So we're going to use all of it up to create that same amount of our acetate. So we've used up all our acetic acid. We have 2 moles of hydroxide left over, and we've also created 4 moles of our weak base over here. So for our concentration then of our hydroxide here, we have 2 millimoles. And for our concentration of our acetate, our conjugate base, we have 4 millimoles. However, when you have a strong base and a weak base, the strong base is going to be the only one that contributes to your equilibrium. So let's take a look at our equilibrium step. So if you have a strong base plus a weak base, the strong will, for lack of a better word, will win out. And that's because all of your strong base is going to contribute way more to the pH than your very weak base that hardly dissociates will. So your concentration then of your hydroxide overall, that's going to be your pOH, and from that you can get your pH. So we need to figure out our concentration of our OH. So the concentration of the OH is going to be 2.0 times 10 to the negative 3rd moles. So remember, that's in millimoles over there. We want it in moles per liter. So we've added 60 milliliters of sodium hydroxide. And then at the very beginning of our problem, it said we had 40 milliliters of acid. So overall, that's 100 milliliters, or 0.1 liters of solution. When you plug this in, you get your calculation to come out to 2.0 times 10 to the negative 3. Or wait, sorry, 2.0 times 10 to the negative 2. Molar. And we know that our pOH equals the negative log of our H plus, or our OH negative concentration, which is this. So negative log of 2.0 times 10 to the negative 2, and that's going to give us 1.7. From that pOH, we can figure out pH. So pH equals 14 minus 1.7. So your pH is equal to 12.3 at the very end. Okay, so now we're going to look at all those points, and we're going to sketch the graph. We're going to sketch the graph of the milliliters of sodium hydroxide added, so that was parts A, B, C, D, and E, versus the pH at those points, and your graph is already labeled for you. Describe the major species at the starting point, the halfway point, the equivalence point, and past the equivalence point. So I'd like you to please pause the video, and I would like you to graph all those points and connect them using a smooth line. Here are my points. I went ahead and just plotted all the points that we figured out before, and we're going to go ahead and label these now. Right here, this is what we call the halfway point. Halfway point. And this point, right in the middle, right there, this is our equivalence point. Let's see why these are important. What is present during our titration at all of these points? So at the starting point, that's right here. At the starting point, the only thing we have is the concentration of acetic acid. We haven't added any sodium hydroxide yet. The only thing we have is our acetic acid. So we have our concentration there. At the halfway point here, we have our acetic acid, and that concentration is going to be equal to the concentration of the conjugate base. So that was this point up here, where we had weak acid equals conjugate base. So at the halfway point, the concentration of our acid was equal to the concentration of our conjugate base. At the equivalence point, we've added just enough base to neutralize all of our acid. And so the only thing we have there is the conjugate base. And then past the equivalence point, the only thing that's going to end up determining our pH at that point is just the concentration of hydroxide. So basically at this point we're just adding hydroxide because there's no more acid. So past equivalence point, you just have hydroxide ions. Alright guys, that is the end of video 5.1.1. Know that was a longer one, but that just walked you through all the steps of a titration.